Welcome back. In our last explainer, we really got a handle on signed and unsigned numbers, how machines deal with positive and negative values. Today, we're going to take the next step. We're moving beyond just storing numbers to how machines actually act on them. We're diving deep into the fundamental logic that underpins, well, every single thing a computer does. This is where the real mechanics of computation begin.
You know, you gotta think about it. Computers don't just sit there holding on to values. They're constantly manipulating data. But here's the key idea, the foundation for everything we're about to cover. When you get right down to the bare metal, to the silicon itself, the most basic action isn't addition or subtraction. It's pure, simple, undeniable logic. Okay, let's really get into this. This shift from thinking in the familiar world of math to thinking in raw logic, it's a huge leap. Bitwise operations are basically the atomic-level tools that computers use to make decisions, to combine different states, and to control the entire flow of information. This is the absolute bedrock of how software works.
To really get this, we have to kind of shift our perspective. On the left, you see arithmetic. That's how we naturally see the world. We see a 5 and a 3, and our brain just goes 8. But a computer, it sees something totally different. It sees the individual bits that make up those numbers. And as you can see on the right, it asks a completely different question. What's the logical result at each and every bit position, one by one?
Now, this bit-by-bit approach has some seriously powerful traits. First off, these operations are ridiculously fast because they map directly to physical circuits in the hardware. They are also incredibly precise. There's absolutely zero ambiguity. But, and this is a big but, that precision comes with a warning. They are so unforgiving. A small mistake won't just crash your program. It'll cause these big, silent, hard-to-find errors.
So let's start with our first logical tool, the AND operation. The best way to think of AND is as the ultimate, strict gatekeeper. It's all about enforcing conditions and making sure that multiple requirements are all met at the exact same time. Just look at this truth table. The output is 0 or false in almost every single case. The only time you get a 1 or true is when input A and input B are both 1. No exceptions, both conditions have to be met. It's like the bouncer at a club. If you don't have both your ID and your ticket, you are not getting in, period. And that perfectly sums up the core job of the AND operation. It's built to answer one fundamental question. Are all of my required conditions satisfied? If even one little part is false, the whole thing is false. So if AND is all about those strict rules, or is its much more laid-back cousin? Or is all about combining possibilities? It's used to check if at least one of many options is available, or if a feature has been turned on from any one of several places. The truth table for OR is pretty much a mirror image of AND's. Notice how permissive it is, right? As long as either input A or input B is a 1, the output is 1. The only way you get a 0 is if both inputs are 0. It's all about accumulation and inclusion, not exclusion. The key takeaway here is that OR answers a much more inclusive question. Is at least one of these conditions true? This is what makes it so perfect for merging different settings together or just checking if any valid state exists in a system. All right, now for an operation that's kind of like a secret weapon in programming. It's often overlooked by people just starting out, but its unique properties make it incredibly powerful for solving some very specific and very important problems in computing. This is the exclusive OR, or, as everyone calls it, XOR. The name kind of gives away its job. Unlike the inclusive OR we just saw, which is happy if one or even both inputs are true, XOR is all about, well, exclusivity. Its main purpose is to detect change or identify when two things are different from each other. Now take a close look at this truth table, because this is what makes XOR so special. It gives you a 1 only when the inputs don't match. A 0 and a 1? Yep, you get a 1. But look at the top and bottom rows. When the inputs are the same, both 0 or both 1, the output is 0. It is the ultimate difference detector. This unique property makes XOR so incredibly useful. It's the magic behind toggling a switch in software. You know, like flipping a setting on and then off again. It's used in simple encryption to scramble data, and it's absolutely critical for detecting errors in data that's flying across a network. So whenever you see XOR out there in code, I want your brain to immediately translate it to this one simple question. Did something change? If the answer is yes, XOR is how the machine knows it.
Okay, our final core operation is actually the simplest of all, not. It does exactly what it sounds like. It takes every single bit in a number and just flips it. All the zeros become ones and all the ones become zeros. The entire value gets inverted.
But do not let that simplicity fool you. Notch can be one of the most dangerous tools in the whole box if you're not careful. Remember signed numbers from last time? Flipping all the bits of a signed number can drastically change its value, turning a small positive number into a huge negative one. A single misplaced not can flip the logic of an entire system upside down.
So we've walked through the four horsemen of bitwise logic, and, or, XOR, and not. So now for the so what? Why does any of this matter? Well, because quite simply, these four operations are running the modern world.
Seriously, they are the gears turning deep inside our operating systems. They manage the data packets flying across our networks. They power the indexes in our databases. They are fundamental to cryptography. They're absolutely essential for performance-critical code in games and simulations. And they even manage control paths in AI systems. They are everywhere. And because they're everywhere, the potential for error is also, well, everywhere. With bitwise logic, precision isn't just a good idea, it is a non-negotiable requirement. So let's look at the absolute most common mistake that even seasoned engineers can make.
This right here is a classic, multi-million-dollar bug just waiting to happen. Confusing the logical and, that's the double ampersand, with the bitwise and, the single ampersand. See, the logical version on the left asks one big question: is this whole idea on my left true, and is this whole idea on my right true? But the bitwise version on the right couldn't care less about big ideas. It performs a logical and on every single corresponding bit of two numbers. They are not the same, and mixing them up leads to absolute chaos.
And this is what makes these bugs so terrifying. A mistake with a bitwise operator usually doesn't cause some spectacular crash with a big error message. Oh no. Instead, it causes the system to just keep on running but with corrupted data or flawed logic. It silently misbehaves, and you might not discover the problem for days, weeks, or even months. You know, ultimately, understanding this logic is what separates a good engineer from a truly great one. It's the key that unlocks how so many complex, high-performance algorithms actually get their incredible speed and efficiency. Without this knowledge, complex code can look like total magic, but with it, you see the gears, and the entire system becomes logical and predictable. So we've laid the theoretical foundation. In our next explainer, we're going to put it all into practice. We'll explore something called bit masks, a really powerful technique that uses these very operations to pack a ton of information, like user permissions or feature flags, into a single efficient number. It's where this raw logic meets real-world system design. Machines don't think like us. They think in bits, and they reason in logic. See you next time.